Okay, so this is going to be the review video for practice test number 4, or for test number 4 for intermediate algebra. I printed off all the problems off the practice test, and we will just work through them like we've done on the other reviews. I will show you how to use the calculator on some bits, and I will show you how to do it on paper as well for various different components. Most of it will be done on paper, just being honest. All right, let's get right into this. The symbol radical, or whatever it is, I mean, I guess I kind of just ruined it for you, is called a radical sign. It's just a terminology that you need to kind of know. The radicand is the stuff that goes underneath it. The radical is the actual sign itself. All right, step 2 is a 4-parter. It says evaluate each radical expression if it is a real number. If it is not a real number, state so. So remember, if there's no little number outside of your radical, then that means it has an index of a 2, or is known as a square root. And we cannot take the even root of a negative number. So we need to keep that in mind. This says radical 484. Now we could do a factor tree and we could figure out what comes out. I mean, obviously looking at it, I know if 4 is going to be a part of it and 4 is a perfect radical, but I'm actually going to test this first on my calculator and just see if it is a perfect square of some kind. And so if you have this calculator, which is the one that is very recommended for this class and all other classes, there is a radical symbol here. You have to click the second button and then click it, and you'll notice, if you can see it in there, which I think you can, that it now has a radical and then it has a blinking box underneath, and you can just type 484. All of that stays under the radical. Hit enter, and then you'll see that that is 22. So the square root of 484 is a perfect square. It's 22, so I know that now moving forward that that is 22. Part B says negative radical 484, but notice the negative is on the let me scroll down. Is on the outside of the radical. What that means is we would take the radical first and then apply the negative. So we just found out radical 484 is 22, so I would get 22 here and then apply the negative, producing a negative 22. It's just like a set of parentheses in that you do what's in the parentheses first and then what's outside. Now C is a totally different problem, because C has the negative under the radical. We can never have a negative under an even-rooted radical and still produce a real number. We can't. So the root is not real. Same thing's true for D. Again, we have the negative under the radical. And you cannot say, oh, well, we have a negative outside and a negative inside. That means they're going to cancel out. No, it doesn't. Because it's not a set of parentheses where you can multiply through your radical like that. It doesn't work like that at all. You have to resolve the radical first and then apply the negative that's on the outside. But we can't resolve this radical because there's a negative underneath it. So again, it is not a real number. All right, 3 says we're taking the cube root of negative 1. There are some squares and there are some cubes that you should really know. Really, you should know your perfect squares from 1 to 10, and you should know your perfect cubes from 1 to 5, because that will greatly help you. But what it's saying is can I take this same thing times itself 3 times and get to negative 1? And the answer is yes, you can, because you can take negative 1 times negative 1, which gives you a positive 1, times negative 1 again gives you a negative 1. So the cube root of negative 1 is simply negative 1. Now, what if you didn't know that, or what if they gave you a harder number than that? You can still do that on your calculator. What you do is there's a caret button. We can call this a caret button, and the green indicator that's behind that is an x radical. That means you get to dictate the index. And so if you click that, oh, nope, that's not the one I wanted. Is that the one I wanted? Let me do 3, and then let me see what it does. Yep. So you have to hit the number first. You have to hit the index first, then second, and that x radical. And that tells it that you want it to have an index of 3 on the outside. Then you can type in negative 1 underneath, and you will see that it calculates it for you. So just in case it does give you a weirder number, you hit your index first, whatever that may be. Don't do it for square roots because you have a square root button, but if it's anything but a square root, you can still use your calculator by hitting the index first, second the x radical, and that'll bump that up to your index. And then you can type in whatever you need to underneath. Oh, see, syntax error. I did something wrong. So on that one. Oh, because I put minus instead of a negative. And see, it'll tell you that. I mean, it doesn't really tell you what you did wrong, but you can kind of figure it out once you do something wrong. Okay, let's move on. All right, oops, so sorry. Don't mean to move it so much. Use the absolute value to simplify. You may need to factor first. So if it says you may need to factor first, then what we're going to do is we're going to actually change this into our fractional exponents and see if we need to have that absolute value or not. If it's an even power up there, we don't really have to have the absolute value. And I don't know why it says use the absolute value, actually. I was really good about, on all these problems, you will never have to type the absolute value symbol in as an answer. So I'm a little confused as to why it says that, because the answer isn't an absolute value at all. So just simplify this, is what it's going to say, or what it should say. If we have z to the 32 and we're taking the square root, remember the index becomes your new denominator. 32 divided by 2 means we have z to the 16th power. Z to the 16th power. And that's our final answer. That's the answer Pearson gives, so I don't know why it said use the absolute value. 5 says assume that all variables represent the positive values and that the radicand is non-negative. So here it already tells us that we get to assume that. I'm wondering if this problem would use the absolute values if this was an odd power, simply because then we could get a negative output, and so then we would need to use the absolute value. But because we have an even power, even if z is odd, or sorry, not odd, negative, like z, if z is -1 and we're taking it times itself 16 times, we're going to, each pairing of 2 is going to make it a positive number, so you're always going to get a positive output anyways. So, sorry, long and short of that. Let's go down to 5. It says simplify. So what we do when we simplify is we look at the number part and the variable part separately. The number part is 64, and we say, okay, is 64 a perfect square? Because that really makes our life easy if it is. And this is, again, why I recommend knowing your 1 through 10 perfect squares, because 64 is a perfect square. 8 squared is 64. So that means you can take the square root, you can actually split this up into where you have 64 times the square root of b10. Well, the square root of 64 is 8. And then b10, we can make that into b10 over 2. We take it into our fractional exponent, which gives us 8b to the 5th, because 10 divided by 2 is 5. So you can split it up into 2 different radicals with a multiplication symbol in between, where you have your number part separate from your variable part, if that's easier for you, so you can see what's actually happening. It's totally up to you. You can also leave them all combined together. Either way, you should get to 8b to the 5th power. 6 says simplify, and we have a quadratic under there, which should tell us it's going to factor. And if we're taking the square root of something, hopefully it factors into a perfect square so that everything goes away. That's what we're hoping for. But what we're going to do is we're going to end up factoring this. And I guess I'll leave it all under the radical for right now. That way we're being the most mathematically accurate here. All right, we got an x squared, so it tells me I have an x and an x term. I have a positive number in front of, or a positive sign in front of my c term. That tells me the signs inside are the same. Since I have a positive in front of my b term, it tells me they're both positives. Now, I need factors of 81 to add together to give me 18. And while there are multiple factors, probably the most common factor of 81 that you should know, if you know your multiplication tables, is 9 times 9 is 81. It's a perfect square. And 9 plus 9 does give me 18. So that means I'm going to put 9 and 9. And notice I wrote the same thing inside of both of my parentheses. That means I could actually rewrite this so that I have x plus 9 squared. The square root of a square like this, remember we could actually write that as, this is one of our rules that we have, where we could pull that power outside, and when you square a square root, they cancel, meaning you're going to be left with just x plus 9. Do not think that you're actually solving this and you're going to get x equals -9. We don't have an equal sign in here. It just says to simplify. So you have to factor. You should get a perfect square situation like this so that it cancels out and you're left with whatever was inside of your parentheses. Okay. 7 actually follows kind of the same rule that we were just doing up here. And if you need the generic rule, I'll write the generic rule, where if you have the nth root of a to the m, that's like saying you have the nth root of a all raised to the m power, which means you have a to the m over n. Like, this is kind of the definition of our fractional exponent and how we're able to go back and forth between our radicals and our fractional exponents. So when I see this, the 6th root of y raised to the 11th power, I know I could actually have that power underneath if I wanted to. But regardless, I know that the 11 on the outside is going to become my numerator, and the index on the outside is going to become my denominator. So I can say that this is going to be a to the 11 over 6, and 11 over 6 doesn't simplify at all. That's my final answer. So there's really not anything for me to do except to know the rule on how to convert from a radical into my fractional exponents. All right. Simplify each radical expression by changing it to its exponential form. Write the answer in radical form when appropriate. That means if we still have a radical in play by the time we're done, aka a fractional exponent, we would write it as a radical. We're not going to write it as a fractional exponent. So again, though, same rule is up here, same rule as this. I have the 5th root of x to the 25th, so that's x to the 25 over 5, but 25 is divisible by 5. It gives me 5. So this simplifies to x to the 5th. There's no radical because there was no fractional exponents left. So that's why I'm able to write it that way. Number 9 is the exact same concept. Exact same style problem. I have the 6th root of x to the 3rd. So the 3 comes on top and the 6 goes on bottom. Now that can simplify. That it simplifies to x to the 1/2. And now at that point it is fully simplified, but it doesn't want us to leave it in a fractional exponent. It says convert back to radical notation. So I need to do that. So radical notation states that this top number is the exponent on the base. The bottom number is the index on my radical. So this ends up becoming simply the square root of x. Now, if you put the little 2 out there as your index, are you counted wrong? No. Are you counted wrong if you put the 1 as your power? I don't think so, but honestly, it's a really bad habit to have putting a power of 1. It just makes it look more complicated, so I recommend not doing that. All right, flip over. Go on to number 10. It says evaluate, if possible, if the expression is not a real number, state so. All right. So we have negative 216, and we have the cube root of that. So here's the issue and the thing that you're going to hate. And honestly, it doesn't matter so much with the cube root. And why did I say cube root if it says 1/3? Because 1/3 means cube root. But here's the issue and the thing you have to be really careful about, and why I'm going to be a little bit of a stickler on this problem and showing you this. It says negative 216 to the 1/3, but notice there's no parentheses around that negative and the 216. That negative is not included in that 1/3. It is not. This is like saying we have a negative 1 times 216 to the 1/3. The only thing being raised to that 1/3 power is the 216. Now, I said it doesn't matter with a cube root, but if this was a square root or an even root, it would make all the world of difference. Because if this said negative 216 to the 1/3, and you stuck that negative under the radical, or to the 1/2, excuse me, and we stuck that negative under the radical, we'd actually be wrong, and we would state that it's not a real answer. But that negative is actually outside of the radical because there's no parentheses to include it with that power. So be so careful about this, okay? This is negative cube root 216, and then we're going to figure out if 216 is a perfect cube or not. So again, with my calculator, I hit a 3, then I hit second, the x radical, and I type 216. And I have 6. So 6 to the 3rd power is 216, which means the cube root of 216 is 6, but then I have this negative outside giving me a negative 6 as my final answer. Now, if I had stuck the negative underneath the radical, because it was an odd root, it would have given me the same answer. But the concept that you're doing is wrong and is incorrect, which is why I made a big point here to show you that that negative is not actually included with that radical. If there was parentheses around it, yes, absolutely. There's not parentheses around that negative. So it needs to come outside of the radical, not go underneath. Be really careful about how your problems are written and presented. It makes a difference. All right, 11 says simplify by factoring. So it says radical 18. Radical 18 is not a perfect square root or a perfect square. So what we're trying to do is come up with perfect squares. And again, this is why it's so important to have a list or know what your perfect squares are. I will make a tiny little reference list, I guess, for you because I've mentioned it now a couple times. So I'm not going to start with 1 because it's kind of pointless because 1 times 1 is 1, no matter how many times you do it. But 2 times 2 is 4, and then we have 3s, 4s, 5s, 6, 7, 8, 9, and 10. So these are the perfect squares. Perfect cubes would be, we multiply these again, so 4 times 2 is 8, 9 times 3 is 27, 64, 125, and that's about where I would stop. But you really should know these because when it comes to simplifying these radicals, knowing these makes it so much easier. Because I'm thinking about, I need to split this up into factors. So what times what gives me 18, but I want those factors to be perfect squares. So I look at my perfect squares, or I think about my perfect squares, and I think, okay, which one of these is a factor of 18? Well, 9 is. 9 times 2 is 18. So this is why it's important to know your common perfect powers when it comes to squares and cubes, because this is like saying we have radical 9 times radical 2. Well, radical 9 is 3. Radical 2 doesn't simplify. Doing cubes is a little bit harder just because we don't play with cubes quite as often. The cube root of 128. So again, though, I made a list of cubes. 125, while it's smaller than 128, that's not going to be a factor of 128. 64, hey, 64 times 2. 64 times 2 would give me a 128. So 64 is a perfect cube that is a factor of 128. So that's like saying I have the cube root of 64 times the cube root of 2. Well, the cube root of 64 is 4. So I'll end up with 4 cube root 2. Now, if we don't have numbers underneath, the way that we do this is we convert it over to our fractional form. And we simplify it that way. Or the way that I think about it is like this. Another way to think about it. I have an index of 2 out here, right? So how many times, like, think of it this way. 7 divided by 2 is what? Well, 7 divided by 2 is 3, right? So that means we'd have x to the 3rd, but then we have 1 x left over, and that one has to stay under the radical. And you're like, I don't know what you just did. Okay, so if you want to take it to the fractional bit, it's going to work like that. And then you're still doing the same thing that I just said, where you're like, okay, 7 divided by 2 is 3, but then we have 1 left over that has to stay under the radical. Another way you can think about it is doing like what we did up here, where we pulled out perfect powers, like we separated them, right? So here, if I have a power of 2 on the index, like my index is 2, then I want there to be something under here that's divisible by 2. Well, 7 is not divisible by 2, but if I remove one of my x's, then I'm going to end up with an x to the 6th, and that's divisible by 2. Because x to the 6th over 2, that's going to simplify to x to the 3rd, and then we just have this radical x that tags along. So there's a lot of different ways to kind of think about how to simplify these radicals when we're talking about just dealing with our variables. And it's really whichever way makes the most sense to you. Honestly, I do this mental stuff most of the time, but if I had to show work, I would do the splitting up thing. Excuse me. Where I'd bump one of my x's over so that I could have an even power under my even rooted radical. So if it's a square root, I just need an even power. If it was a cube root, I would want something that's divisible by 3. If it's a fourth root, I'm hoping for something that's divisible by 4. I mean, that's how this is going to work. And we get to see a fourth root on the next example. So really, we can think about these all individually. And if it helps you to split them up so that you have a number radical and a variable radical and another variable radical, then do that. Whatever is going to work best for you. I think I'll do that on this one just to show you excuse me, what I mean by that. So I'm going to take the fourth root of 32 times the fourth root of x to the 12th times the fourth root of y to the 9th times the fourth root of z to the 19th. So all I did was split everything up. The numbers and each of the variables have their own radical. And then I'm trying to figure out, okay, is 32 a perfect fourth? And obviously I didn't go to fourths whenever I made my list. But if I wanted to go to fourths, I would just take my thirds and multiply it again by each of them. So this was my 2's. So 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So this would be a fourths column, perfect fourths. Well, 16 times 2 is 32. So I can actually I do have a perfect fourth in there. So this would be the fourth root of 16 times the fourth root of 2. So I've just split my number part so that I have a perfect fourth underneath the fourth root. That way it will simplify. Here, what I'm going to do with my variables is I want the powers on these variables to be divisible by 4. X is already that way. 12 is divisible by 4, so I don't need to do anything at all to my x's except rewrite it with my fractional exponent. That's a 4. My other ones, I need to separate them out kind of like I did my number in such a way that the power is divisible by 4. So what's the biggest number that's divisible by 4 that's less than 9? So it's kind of like the Price is Right. How close can I get there without going over? Well, 4 times 1 is 4. 4 times 2 is 8. 8 is as close as I can get. So this is going to split up into the fourth root of y to the 8th times the fourth root of y, because y to the 8th and y will give me back to y to the 9th. I do the exact same thing for z to the 19th. I can't go over though. So like 4 times 5 is 20, and that's really close to 19, but I went over, and I can't do that. So I need to think about 4 times 4, which is 16. So it means this is the fourth root of z to the 16 times the fourth root of z to the 3rd, because 16 and 3 will take me back up to 19. So now each of these has a component that's going to simplify. This is going to simplify, this is going to simplify, this is going to simplify, and this is going to simplify. Everything else is going to end up staying under the radical. How do I know that? Because 2 is not a perfect fourth. And because the powers on these remaining variables are less than 4. That's one of the rules and how I can tell when something is simplified. The fourth root of 16, well, 16 is 2 to the 4th. So the fourth root of 16 is 2. So I dealt with this one. Then I go to the next circled thing. x to the 12 divided by 4, well, 12 divided by 4 is 3. That gives me x to the third. I've dealt with that one. Here I have y to the 8th to the 4th root. Well, if you need to write it down, that'd be y to the 8 divided by 4. 8 divided by 4 is 2. Lastly, I have z to the 16th. I'm taking the 4th root of that. That means I'm taking 16 divided by 4, which gives me z to the 4th. Those are all the bits that are outside of our radical now. We were able to pull all those out. Anything else just goes back underneath. And we can shove it all underneath the 1/4 root radical. We have a 2, we have a y, and we have a z to the third. This big O bad boy is the final answer. And again, the way you know is you check your number, make sure it's not a perfect power, and it's not, and then you check to make sure that the exponents on your variables are less than your index. If that is true, then your radical is simplified. All right. Let's flip over to the next one. Simplify the following expression. Says this is combining like terms. It's using addition with our radicals, addition and subtraction. And remember, with addition and subtraction of radicals, you have to have two things. You have to have the same index on your radical. That's the same little number outside. And you have to have the same radicand, aka the same number underneath. If you don't have both of those things, you cannot add and subtract the radicals. So I have 4 radical 3 minus the cube root of x plus 7 radical 3 plus 6 cube roots of x. So I have square roots of 3 that are the same. So I can do that addition. And what I do is it's a lot like adding fractions, in that with fractions, if they have the common denominator, we don't do anything with the common denominator. We just add the numerators. So we're not going to do anything with the radical bit. We're just going to add the coefficients up front. 4 plus 7 is 11. 11 what? 11 radical 3s. The radicals almost act like a variable of sorts, where it's almost like, okay, we had 4x and 7x. What do we have? Well, we have 11 x's. It's just that our x's aren't x's. It's radical 3. All right, so we added those, and then I do have negative cube root of x plus 6, or cube roots of x. Those have the same index and the same radicand, so I can do that subtraction of negative plus 6, which will produce a plus 5 cube roots of x. And that's all I can do with that. These are not like radicals, so I can't do anything further with them. This is fully simplified, and that is all I can do. Now, when we multiply radicals, I don't have to have quite as many stipulations. The only thing that has to exist for me to do multiplication with radicals is they have to have the same index, aka the same small number on the outside. So as long as they have that, then I can do the multiplication. And in this case they do, because I have the cube root and the cube root. So it'd be the cube root of 10 times 4, which is 40. And then we're going to always be careful, because it says multiply and simplify. So is 40 a perfect cube? And the answer is no. It does not live on our perfect cube list. But is there a factor of 40 that does? Well, 8 times 5 is 40. So 8 is a perfect cube. So yes, there is a perfect cube factor. This is like saying we have the cube root of 8 times the cube root of 5. Well, the cube root of 8 is 2. 2 cube roots of 5 will be our final answer. And yes, I'm writing a lot of these outside of the answer box just simply so you can actually read them. All right, 17 says to multiply. And again, the first thing we want to make sure is that all of our indexes are the same. And in this case, they are, because they are all square roots. Now, we have one term outside and 2 terms inside. We always want to make sure we can't do anything with the 2 terms inside first. And in this case, we can't, because it's a subtraction inside. And we need the same radicand and the same index, and we don't have those. So this is a distribution problem. We're going to take radical 3 times radical 3, giving me radical 9. Radical 3 times negative radical 5 gives me a negative radical 15. And then we think, okay, well, I know radical 9, that's 3. So I'm going to end up with 3 minus radical 15. Radical 15 doesn't simplify at all. The only factors of 15 are 3 and 5, and neither of those are perfect squares. So that's all we can do on this one. (18) is a FOIL problem. We have a binomial times a binomial, so we have to FOIL it. And we are going to check, okay, we have the index of 2, so it's not going to cause any problems. We're going to be good there. So foiling, I do my first, radical 7 times radical 7, that's radical 49. I do my outer, so I have radical 7 times negative x. That negative x is going to act like a coefficient, so it comes out front, and then we have radical 7. Remember, you can't multiply like a whole number by the radicand like that. It just comes out front of it. My inner is a positive x times radical 7, so that'll be a plus x radical 7. And my last will be an x times negative x, giving me a negative x squared. Now, look what happened here in this middle bit. I have a negative radical, or negative x radical 7 and a plus x radical 7. Those cancel out. And radical 49 is 7. We actually had a difference of squares here. We really did. It's just we're not used to that because 7 is not a perfect square in our mind. But radical 7 times radical 7 would produce 7, so it is theoretically a perfect square in that way. Same exact thing's happening here on 19. Same exact thing. It says multiply. We have 7 minus radical 5. We have 7 plus radical 5. If you have the same numbers but your signs are different, it's a difference of squares. So our middle two terms had better cancel out just like last time. So my first would be 7 times 7, which is 49. My outer would be 7 times radical 5, which is 7 radical 5. My inner would be a negative radical 5 times 7, giving me a negative 7 radical 5. And my last is a negative radical 5 times positive radical 5, giving me a negative radical 25. And just like last time, these bits cancel out. So I have 49, and then minus whatever radical 25 is. Radical 25 is 5. 49 minus 5 is 44. So this one we actually just get a single number because there was no variables at play in our binomials, so there was nothing left for us that was unknown. All right, number 20, we have to rationalize our denominator. Remember, a fraction is never simplified if you have a radical in the denominator. So what we have to do is we have to rationalize it. How do we rationalize it? By multiplying by the conjugate. We have 3 plus radical x. The conjugate of that is the exact same thing, but we just changed the middle number. That is the only thing that changes, is that middle number. If it's a plus, it becomes a minus. If it's a minus, it becomes a plus. Nothing else changes. If this said negative 3 plus radical x, then the conjugate would be negative 3 minus radical x. No other signs change. This sign in the middle is literally the only one that changes. And I don't want to circle it because I don't want to mess it up. So I'm going to multiply the top and bottom by the conjugate, which is 3 minus radical x. The reason why this works is because if you look at these bottom numbers, we're taking 3 plus radical x times 3 minus radical x. Guys, that's no different than what we did on the last two problems. It's a difference of squares situation. So the middle terms are going to fall away, and you'll notice that neither one of these problems that we did up here, we had a radical as our final answer. That's why multiplying by the conjugate works. So on top, I'm just distributing that 8. 8 times 3 is 24. 8 times a negative radical x will be a negative 8 radical x. On bottom, I FOIL. My first, which I'm going to do in red, I guess, so you can see it because I have to mark through stuff. First is 3 times 3, which is 9. My outer is 3 times negative radical x, which will give me negative 3 radical x. My inner is radical x times positive 3, giving me plus 3 radical x. My last will be radical x times a negative radical x, giving me a negative x, radical x squared. Now, some of you might be thinking, okay, if we know those middle two terms are canceling out, do we have to actually do this step? The answer is no, you don't. I'm showing you all the steps. If you're comfortable skipping some, skip them. Go for it. So I have 24 minus 8 radical x on top, and I have 9 minus, well, x squared, square rooted is x. This is my final answer. There's nothing else I can do with it. That's all I can do. I multiplied both the top and bottom by the conjugate, and I simplified where I could. All right, let's flip over. Solve if the equation has no real solution, state so. So the goal here is to get the radical by itself, and that's how we're going to do this. Now I'm going to do it on a separate sheet of paper because obviously there's just not a lot of space over here, and that way I can show you all the steps. Luckily for us, this one is written so that the radical is already by itself. We have radical 4x plus 5 equals 7. It's already by itself. So what we're going to do is we end up squaring both sides. Whatever the index is on your radical is what you end up doing. So if it's a cube, you're cubing it. If it's a square root, you're squaring it. Because what ends up happening is the square cancels with the radical, leaving us with just 4x plus 5. 7 squared is 7 times 7, which is 49. Now I have a really basic equation that I'm just going to solve. Subtract the 5, 4x equals 44, divide by 4, and I get x equals 11. Now, in a traditional problem, we would be done and we'd say, yay, x equals 11. This is a radical problem though, so you have to check your work. It is non-negotiable. It's not like this is a good thing you should do just to make sure you did it right. No, you have to check it because you can get things known as extraneous solutions, as we've seen. And we don't want to get extraneous solutions. So we have to plug 11 back into the original and make sure it works. So I'm going to come over here and I'm going to do my check. 4 times x, well, x was 11, plus 5 equals 7. 4 times 11 is 44. 44 plus 5 is 49. 49 square rooted is 7. So it works. So our answer is correct. Our answer was x equals 11, so that is what I put in my answer box. You have to check your answers. 22, same exact thing, only it's not quite ready for us yet. The radical is not isolated. We have radical y plus 6 minus 1 equals 2. To get the radical by itself, what I'm going to have to do is I'm going to have to add that 1 over. So I have to do an additional step before we can do the rest of it. But honestly, once we get to this step, it is no different than the last problem. I'm doing a square root, so I'm going to end up squaring both sides. It means it'll be with y plus 6 equals 3 squared, which is 9. To solve for y, I subtract 6, and I get y equals 3. And again, I'm going to plug it into the original problem, not the one I've moved around, but into the original problem to make sure it works. So radical y, well, y was 3 plus 6, and then I have the minus 1 outside equals 2. 3 plus 6 is 9. Square root of 9 is 3. 3 minus 1 is 2. So it does work. But we always have to check, because if it didn't work, if we got a false statement, then instead of writing that y equals 3 in here, we would end up having to pick that there is no real solution, which can happen, and it only happens if you actually check your work. So that's why it's so important that we don't just stop because we think, oh, well, we found an answer, we get to be done. No, you have to check your work.